Hey everyone, welcome back to another study live session. Let's continue studying from where we left off in the previous study live session. Without wasting any time, let's get started. Proceeding is looking at the electron potential. Electron potential is a bit of how even below the standard electrochemicals. We have seen that different metal combinations have different values of electron potentials. The various elements can be arranged in order of increasing or decreasing values of the reduction potentials. The arrangement of various elements and the order of increasing values of standard reduction potentials is called electrochemical. The electrochemical series, also called activity series, consisting of some electrodes along with their respective reduction reactions as given. Applications of electrochemical series. Activity of metals. Lower the standard reduction potential value, higher will be the activity of metal, as it will have higher tendency to lose electrons. Lower the standard reduction potential value, higher will be the activity of metals, as it will have higher tendency to lose electrons. Lithium, potassium, sodium, zinc. Predicting whether a metal can liberate hydrogen from an acid or not. All those metals whose reduction potential are less than hydrogen, that is, have negative values, will have higher tendency to lose electrons than hydrogen, and so H plus ions will gain electrons from H. Predicting feasibility of redox reaction. A redox reaction is feasible only if the species having higher reduction potential is gaining electrons and the species to release electrons must have lower reduction potential. For example, COS plus 2Ag is equal to CO2 plus 2Ag. Here Ag have higher reduction potential than copper, therefore Ag plus is reduced here. In an electrochemical cell, the electrode having a lower reduction potential will act as anode, because it will have a higher tendency to lose electrons and lower tendency to gain electrons. And the electrode having a higher reduction potential will act as cathode, because it will have a higher tendency to gain the electrons and lower tendency to lose the electrons. Calculation of EMF of the cell. Every galvanic or volatile cell is made up of two half cells, the oxidation half cell anode and the reduction half cell cathode. The potential of these half cells are always different. The difference in potentials of the two half cells is known as the electromotive force. EMF, electromotive force. The standard EMF of the cell is E0 cell. May be obtained by subtracting the standard electrode potential of the anode from that cathode, that is E0 cell equals to standard electrode potential of cathode minus the standard electrode potential of anode. E0 cell equals to E0 cathode minus E0 anode. The standard electrode potentials are very important, and we can get a lot of other useful information from them. The values of standard electrode potentials for some selected electrode processes, that is reduction reactions, are given in the table. Standard electrode potentials is 298 level. Ions are present as aqueous species, and H2O as liquid. Gases and solids are shown by G and S respectively. Let's go over a quick mind map of redox reactions and let's get done with the chapter. It's starting now, reading the same chapter. The redox reactions in terms of electron transport, special cases of oxidation number. Then we have fractional oxidation states, types of redox reactions. Classical concept of oxidation and reduction, redox reactions and electron process, balancing of redox reactions, oxidation number method, and oxidation number, rule for deriving oxidation number. This is the whole subject, redox reactions. Now let's go to thermodynamics. Measurement of delta U and delta H calorimeter. We can measure energy changes associated with chemical or physical process by an experimental technique called calorimeter. In calorimeter, the process is carried out in a vessel called calorimeter, which is immersed in a known volume of liquid. Knowing the heat capacity of the liquid in which calorimeter is immersed and the heat capacity of calorimeter, it is possible to determine the heat evolved in the process by measuring temperature changes. Measurements are made under two different conditions: at constant volume QV and constant pressure QP. Delta U measurements. For chemical reactions, heat absorbed at constant volume is measured in a bomb calorimeter. Here a, Here a steel vessel, the bomb, is immersed in water bath. The whole device is called calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost to the surroundings. A combustible substance is burnt in pure dioxygen supplied in the steel bomb. Heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Since the bomb calorimeter is sealed, its volume does not change. That is, the energy changes associated with the reactions are measured at constant volume. Under these conditions, no work is done as the reaction is carried out at constant volume. Work done will be zero as the reaction is carried out at constant volume. In the bomb calorimeter, even for reactions involving gases, there is no work done as delta V equal to zero, that is volume equal to zero. Temperature change of the calorimeter produced by the completed reaction is then converted to QV by using the known heat capacity of the calorimeter with the help of the equation. Q equals to C into M into delta T, which equals to C into delta T. C into M into delta T, which equals to C into heat capacity. C is heat capacity. Here, like we said in the previous thing, C stands for heat capacity as well as it itself. Specific heat capacity. This is C. More about heat capacity. Okay. Heat of a system in constant pressure and temperature is called. Heat capacity of the calorimeter. Calorimeter is determined by using a known weight of a given chemical substance prior to the manual experiment. The heat combustion of benzoic acid is 3226 kilojoule per mole. The theta is the rise in temperature of water in calorimeter after complete combustion of the experimental substance. The weight of the substance is n grams. The molecular weight is m. The heat capacity of the calorimeter plus water total calorimeter system is Z. The heat of combustion delta equals to Z into theta into molar mass per weight of the substance equals to minus negative kilojoule per mole. With theta equals to T2 minus T1. With capacity of bond separately given Q equals to Q bond plus Q water x Q bond delta T2 water into C water delta T. This is for water. If ice is given in the bond, then Q is evolved heat equals to delta H fusion ice into number of moles of water formed, and Q evolved equals to L fusion ice into mass of water formed in grams. In the above experiment, the volume is constant. Hence, heat of combustion is at constant volume. QV is converted to QP using the equation QP equals to QV plus delta NGR. That is delta H combustion equals to delta E combustion plus delta NGRT. Ng is change in the number of gas molecules in the combustion reaction. T equals to T1, T equals to experimental temperature. Delta H measurements directly delta H. Measurement of heat changes at constant pressure. General under atmosphere can be done by a calorimeter shown in the diagram. We know that delta H equals to delta QP at constant pressure, and therefore heat absorbed or evolved. QP at constant pressure is also called the heat or reaction of enthalpy or reaction or is called the heat of reaction or enthalpy of reaction. Delta RH. Delta RH is enthalpy of reaction. In an exothermic reaction, heat is evolved and system loses heat to the surroundings. Therefore, QP will be negative and delta RH will also be negative. Similarly, in endothermic reaction, heat is absorbed, QP is positive and delta RH will be positive. Definition of water equivalent WE capsule. The amount of water that would absorb the same amount of heat as the calorimeter per degree temperature increases. For this water at high temperature T2 Celsius of known mass M2 and water at lower temperature T1 degrees Celsius and mass M1 varies. These two are mixed in the calorimeter and the resultant temperature T3 naught C is noted. W equals to M2 T2 minus T3 by T3 minus T1 minus of M1. Heat liberated equals to W plus volume of reaction mixture into rising temperature into specific heat capacity of water. Calorimeter for measuring heat changes at constant pressure. Atmosphere work done calculation in reactions. In chemical change reactions, work done equals to minus of delta NGRT. If delta Ng equals to 0, W also equals to 0. Delta Ng equals to negative, W equals to positive, that is work done on the system. Delta Ng equals to positive, that is work done equals to negative, work done by the system. In fission and allotropic change reaction, work done equals to minus of delta NGRT. If delta Ng equals to 0, check work done by delta V side. C graphite gives rise to C diamond. Delta Ng equals to 0, but delta V equals to negative, therefore work done is positive. That is work done on the system. Thermochemistry. It is a branch of chemistry which deals with the heat changes occurring during the reaction. Thermochemistry is based on first law of thermodynamics. Exothermic and endothermic reaction. Exothermic reaction, a chemical reaction. Exothermic reaction, HR is greater than HB. It is delta H equals to HB minus of HR, product minus reactants. Therefore, delta H equals to negative. Example of nitrogen and carbon. Endothermic reaction, a chemical reaction which occurs with the absorption of heat from the surroundings is known as endothermic reaction. In endothermic reactions, product is greater than reactants. Here, product is less than. So it's addition. HV minus HR. Enthalpy of reaction. It is the amount of heat absorbed or evolved when the reactants are converted into products according to stoichiometric equation at constant temperature. Two types of enthalpy reactions. QP equals to delta H equals to delta RH at constant pressure and temperature. P equals to Q which equals to U which equals to delta U RU at constant volume and temperature. Enthalpy change delta H of a reaction. Reaction enthalpy. In a chemical reaction, reactants are converted into products and is represented by reactants to products. The enthalpy change accompanying a reaction is called reaction enthalpy. The enthalpy change of a chemical reactions is given by delta RH. Delta RH equals to sum of enthalpies of products subtracted by sum of enthalpies of reactants. Here summation sigma is used for summation and AI, BI are the stoichiometric coefficients. Given in the balance chemical equation, for example, for this reaction, I think. Where HM is molar enthalpy. Enthalpy change is a very useful quantity. Knowledge of this quantity is required when one needs to plan the heating or cooling required to maintain an industrial chemical reaction at constant temperature. It is also required to calculate temperature dependence of equilibrium constant. Standard enthalpy of reactions. Enthalpy of a reaction depends on the conditions under which a reaction is carried out. It is therefore necessary that we must specify some standard conditions. The standard enthalpy of reaction is enthalpy change for a reaction when all the participating substances are in their standard state. The standard state of a substance at a specified temperature is its pure form at 1 bar. For example, the standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar. Standard state of solid iron at 500 Kelvin is pure iron at 1 bar. Usually data are taken at 298 Kelvin. Standard conditions are denoted by adding a superscript to the symbol delta H. Factors affecting the enthalpy of reaction. The heat of the reaction depends on physical states of reactants and products. Stoichiometric equations. Allotropic forms. Pressure. Constant pressure, volume, concentrations of solutions, temperature of the reaction. Effective temperature on heat of reaction can be explained by Kirchhoff's equation. Enthalpy changes during phase transformations. Phase transformations also involve energy changes. The ice, for example, requires heat for melting. Normally, this melting takes place at constant pressure, atmospheric pressure, and during phase change. Temperature remains constant at 2 centigrade Kelvin. Here, delta fusion H minus is enthalpy of fusion in standard state. If water freezes, then process is reversed and equal amount of heat is given off the surroundings. The enthalpy change that accompanies melting of 1 mole of solid substance in standard state is called standard enthalpy of fusion or molar enthalpy of fusion. Delta vaporization is the standard enthalpy of vaporization. Delta vap H minus is the standard enthalpy of vaporization. Amount of heat required to vaporize 1 mole of a liquid at a constant temperature and under standard pressure 1 bar is called its standard enthalpy of vaporization or molar enthalpy of vaporization. Standard enthalpy changes for different types of process based on the UPSC recommendations. Melting of a solid is endothermic, so all enthalpies of fusion are positive. Water requires heat for evaporation at constant temperature of its body. boiling point Tb and the constant temperature. The standard enthalpy of sublimation is delta sub H minus, and standard enthalpy of sublimation is the change in enthalpy when 1 mole of a solid substance sublimes at a constant temperature and under standard pressure. Sublimation is direct conversion of solid into its vapor solid. Solid CO2 or dry ice sublimes at 195 Kelvin with delta sub H minus plus 25.2 kilojoules per minute. Naphthalene sublimes slowly, and for this delta sublimation is 73. The magnitude of the enthalpy change depends on the strength of the intermolecular interactions with the substance undergoing the phase transformations. For example, the strong hydrogen bonds between water molecules hold them tightly in liquid phase. For an organic liquid such as acetone, the intermolecular force dipole-dipole interactions are significantly weaker, thus it requires less heat to vaporize 1 mole of acetone than it does to vaporize 1 mole of water. One example. Standard enthalpy of formation. Standard enthalpy change for the formation of 1 mole of a compound from its element in their most stable states of aggregation, also known as a reference state, is called standard molar enthalpy of formation. Its symbol delta F is where F is the subscript F indicates that 1 mole of the compound under question has been formed in its standard state from its elements in their most stable states of aggregation. The reference state of an element is its most stable state of aggregation at 25 degrees Celsius and 1 bar pressure. For example, the reference state of dihydrogen H2 gas and those of dioxygen, carbon and sulfur O2 gas. Simulation with standard molar enthalpies of formation are given. Delta F of H is equals to minus 225 It's important to understand that a standard molar enthalpy of formation, delta FH minus, is just a special case of delta RH where one mole of a compound is formed from its constituent elements, as in the above three equations for 1 mole of each water, methane, and ethanol. Response. In contrast, the enthalpy change for an exothermic reaction CaO plus CO2 gas gives rise to CaCO3. Delta RH minus equals to minus of 178.3 kilojoule mole inverse. Is not an enthalpy of formation of calcium carbonate since calcium carbonate has been formed from other compounds and not from its constituent elements. Also for the reaction given below, enthalpy change is not standard enthalpy of formation. Delta F H minus for HBr is delta R is minus 72.8 kilojoules. The 2 moles instead of 1 mole of the product is formed from the elements, that is delta RH minus equals to 2 of delta FH minus. Therefore, by dividing all coefficients in the balanced equation by 2, the expression for enthalpy of formation of HBr is written as by convention. Standard enthalpy for formation delta FH minus of an element in reference state, that is its most stable state of aggregation, is taken as 0. Suppose you are a chemical engineer and want to know how much heat is required to decompose calcium carbonate to lime and carbon gas with other substances in the standard state. CaCO3 gives rise to CaO plus CO2 gas. Here we can make use of standard enthalpy of formation and calculate the enthalpy change of the reaction. The following general equation can be used for the enthalpy change of reaction. That is, summation of the stoichiometric values of the products minus of summation of the stoichiometric values of the reactants. Where A and B represent the coefficients of the products and reactants in the balanced equation. Let us apply the above equation for decomposition of calcium carbonate. Here coefficients A and B are 1 each. Therefore, delta RH plus equals to delta FH minus. Same 178, 178. Here it's positive, over there it's negative. Thermal equation is of constant summation. Thus, the decomposition of CaCO3 is an endothermic process, and you have to heat it for getting these values. Formation of CaCO3 is an exothermic process, whereas dissociation of CaCO3 is an endothermic process. Nice. If the standard heat the standard heat of formation is negative, the compound is called exothermic compound. If the standard heat of formation is positive, the compound is called an endothermic compound. Exothermic compounds are thermodynamically more stable than endothermic compounds. The following general equations can be used for enthalpy change calculations. Enthalpy change calculations. Reactants formed, and again reactants. Nice. Thermochemical equations. A balanced chemical equation together with the value of its delta RH is called a thermochemical equation, which specifies the physical state along with allotropic state of the substance in an equation. The above equation describes the combustion of liquid ethanol at constant temperature and pressure. Constant temperature and pressure. The negative sign of enthalpy change indicates that this is an exothermic reaction. It would be necessary to remember the following conventions regarding thermochemical equations. The coefficients in a balanced thermochemical equations refer to the number of moles, never molecules, of reactants and products involved in the reaction. The numerical value of delta RH minus refers to the number of moles of substances specified by an equation. Standard enthalpy change, delta RH minus, will have units of kilojoule mole units. To illustrate the concept, let us consider the calculation of heat of reaction for the following reaction. Note that the coefficients used in these calculations are pure numbers, which are equal to respective stoichiometric coefficients. The unit delta RH is kilojoule, which means per mole of reactions. Once we balance the chemical equations in a particular way, as above, this defines the mole of reactions. If we had balanced the equation differently, then this amount of reaction would be 1 mole of reaction and delta RH minus will be this big. It shows that enthalpy is an extensive quantity. Enthalpy is an extensive quantity. When extensive, it depends on this. When a chemical equation is reversed, the value of delta RH minus is reversed in sign. Plus becomes minus, minus becomes plus, but the number values do not change. Like the formation of ammonia, N2 by 3 plus of 3H2 gives rise to 2NH3, but the time the heat released is minus 91.8 kilojoules. This formation of ammonia into gas plus of 3H2 gas gives rise to 2NH3 gas, and the heat evolved is 91.87 kilojoules per joules per mole. When the ammonia itself is split into 3H2 gas plus N2, then the heat evolved delta RH equals to plus of 91.8 kilojoules. He's of concentration. Well, that was all about chemistry. We did go through redox reactions and thermodynamics. Thermodynamics, they hold the thermodynamic chemical equation, thermochemistry, and all etc. calculations. So with that, we'll wind up this study live session and see you soon in the next study live session. Till then, keep studying. Happy studying. Bye.